on a cruise boat, using electricity, or flying high above the clouds, you've been powered by one of those gas turbines. Here we see the basic components of a gas turbine: the compressor, the combustion chamber, and the turbine, which through the central shaft powers the compressor. Turbines and compressors have different designs. In our case, the compressor is a radial design.
And the turbine in our case is actually an axial turbine.
Let's take a flight through the Rolls-Royce Trent 900 used in the Airbus A380, the largest passenger aircraft in the world. The path we just followed was the same path as the air particle would take through the turbine. Now looking from the side, we see that the turbine consists of several stages of blue stators followed by red rotors. Both are designed similar to airplane wings, having their cross-section resembling an airfoil, providing lift when moved relative to the airflow. Since a major part of the turbine's purpose is to drive the compressor, which is mounted on the same shaft, a compromise has to be made between the efficiency of the compressor and the efficiency of the turbine, which have their optimums at different RPMs. This makes the rotational speed a major design point. The incoming flow from the former stage with the velocity c1 is deflected by the blue stator, which also acts like a nozzle, resulting in a higher exit velocity c2. The red rotor revolves at the rotational speed u2, resulting in the relative velocity w2. W2 then becomes the entering speed of the airflow in the following rotor. This process continues throughout the whole turbine. Visualizing the different velocity components is commonly done using these triangles, hence being called velocity triangles. Having said that the rotational speed of the rotor is a major design point of the turbine, the angles alpha and beta serve as tools to accomplish the design point. The angles are influenced by the orientation and geometry of the blades and are therefore two of the major design parameters for turbine engineers. Just like the wings of an aircraft, the blades are aerodynamically shaped profiles. One issue when sizing either aircraft wings or rotor blades is the development of boundary layers, which eventually can lead to stall. In this case, the efficiency is decreased and in worst case eventually can result in engine failure. This results in limiting the values for the angles alpha and beta. The way one sets alpha and beta also affects the pressure drop in energy extraction. In fact, let's take a look on how energy actually is extracted from the turbine.
Using the ideal gas law, we can easily see where the work is coming from. The addition of fuel results in an increase of temperature and therefore allows for the extraction of energy. To show the connection to the blade design though, we need to derive some further equations, known as the Euler equations. We start with some fundamental equations. The conservation of energy, conservation of angular momentum, and the definition of work. Now, let's do some magic!
And I know that sometimes
So now we have some equation, the Euler equation, which actually puts the velocity components into relation with the extracted energy. Just remember the velocity triangles we had from before.
Depending on where the pressure drop occurs, the blade design is referred to as impulse or reaction. In a blade of the impulse type, the pressure drop occurs only in the convergent stator. The change in cross-section results in a change of velocity and therefore pressure drop. Its counterpart works exactly the opposite way. In a turbine with reaction blading, the pressure drop takes place in the convergent rotor, whereas the stator only functions as a guide vane. The chosen design varies from stage to stage, as the high pressure stages at the inlet of the turbine are normally of the impulse design in order to extract maximum energy at high RPM. The successive low pressure stages are of reactional type in order to extract energy at maximum efficiency at lower RPMs. Let's take a look at the entire system from a thermodynamic perspective using the PV and the TS diagrams. It's here where we can see the overall thermal efficiency of the engine. In an ideal case, the cycle will look like this. Beginning in the compressor, the temperature and pressure are increased while the volume is decreased. This is called an isotropic compression. In the combustion chamber, fuels added, increasing the temperature and entropy in an isobar process. When the air reaches the turbine, an isentropic expansion occurs. An important parameter to evaluate when talking about thermodynamics is the thermal isentropic efficiency. This efficiency is a ratio between the produced work and the added heat. However, we are not living in an ideal world, and neither do the gas turbines. Aerodynamic effects, friction and pressure drops lead to losses, which shift the lines away from the idle process. The formerly idealized processes are neither completely isentropic nor isobar. The actual efficiency can now be described by this equation, where kappa is the isentropic exponent, which describes the heat capacity properties of the gas.
In order to wrap up today's session, I would like you to recall the key elements of today's video. The main purpose of axial turbines is to extract energy from the airflow. This is done by a consecutive set of stages, each consisting of stator and a rotor. Sizing those components is done by using velocity triangles and the angles alpha and beta, which serve as major design parameters. The Euler's equation is putting the extracted work into relation to the velocities, which makes it one of the major tools when designing a blade. But just keep in mind, when we're designing a turbine, we're doing it for the real world. Therefore, friction and thermal effects do influence our efficiency and therefore our design. Remember, where fuel is added, this added energy is extracted by We will start by deriving some fundamental equations now. First, we have the definition of fuck. In order to wrap up today's session, I would like you to recall the key factors of key elements. What the fuck? The major purpose of an axial turbine is to extract energy from the airflow. What's so fucking funny?
I don't know.
But just keep in mind, when we are designing a turbine, we're doing it for the real world. So friction and thermal effects. Oh, fuck it. When we are designing a turbine, we're doing it for the real world. So effects like thermal, fuck it. Sizing those components is done by using velocity profiles, velocity triangles, but we can't cut that in two. The Euler's equation is putting the extracted work into relation to the velocity triangles. Don't you see when I'm moving?
I think I'm more listening than...
Let's just cut here.